let's go for it then. Cool. So yeah, so I'm going to be talking about balance and causal inference from sort of simple methods like post-stratification to some of the fancier stuff, like the stuff based on regularized Riesz representers. And this talk is based largely on my paper, Augmented Minimax Linear Estimation with Stefan. So let's get started. Okay, there, all right. So we're going to start with an example that I hope is familiar to many of you all, estimating the treatment-specific mean. So the idea is we're going to observe IID units described by covariates, which we'll call X, a level of treatment, which we'll call W, and an outcome, which is the outcome under that level of treatment. When treatment assignment is unconfounded, the treatment mean is just an average involving the regression of y of x on w. And we're going to call this regression m of x on w, of x and w. In particular, it's the average of the treated arm value. M of x is the sort of natural value of the covariate with the treatment set to the particular treated arm, which is 1.
Looks like we're having some connection issues here.
Some difficulty. Okay, looks like we lost Skip or David, so maybe let's wait a few minutes, see if he comes back. Let's see.
Well, this is actually the first time we've had a speaker having technical difficulties, which is not bad, given the number of times we've done this now.
Yeah.
No, it's pretty amazing.
Yeah.
So here he might be able to join by phone, which hi, David.
Great. Okay, I apologize. I'm having some internet connection issues apparently.
If you want, if you don't share your video, maybe that will make it less likely to happen. And there's also
a disconnect and not a lag, but I can totally. Okay.
All right.
There we are. Okay. So I think this is where we were at. So we observe this, and we're trying to estimate this guy. All right. So let's talk about sort of some basic estimation approaches. And the first is real obvious. So if we want to estimate the average of the treated arm value of the regression function, we just find an estimator for the regression function, and we average its treated arm value over the sample. So this is often called imputation. So another approach which is common but a little less obvious is weighting. We can find weights that will approximately equate averages of the treated arm value of m with weighted averages of the natural arm value. That is, they solve this condition. And so the idea is, because we basically observe this quantity through y, that solves our problem. We take a weighted average of the observed outcomes y, which are just the natural arm value plus noise, and that's our estimator. And so it may not be trivial to estimate weights with this property, but certainly there exist weights with this property. In particular, the inverse propensity weights will do. Because for each square integrable function m, the population analog of this condition is satisfied. That is satisfied in mean. And so what the inverse propensity weights do is they have this indicator that sort of picks out the correct arm of treatment. And we have the conditional probability that means that its conditional mean is 1. So we're not sort of inflating anything by doing that, or losing anything by doing that. All right, so these are our sort of basic approaches, but let's look at something a little fancier, augmented inverse probability weighting. So imputation works pretty well if we estimate the regression function well, and weighting works if we estimate the inverse propensity weights well, but combining both yields a more robust estimator, AIPW. And the idea is pretty simple. We're going to start with the imputation estimator, and then estimate its error by weighting our regression residuals and then subtract it off. So here's our imputation estimator, and here's our estimate of its error. And this weighting estimate of its error works essentially just like before. The idea is that the error of the imputation estimator is just the average of the treated arm value of the regression error function. That is the difference between our regression function estimate and the regression function itself. And the regression residuals are just its natural arm value plus some noise. And that's what our weights do. They equate natural arm values with treated arm values. So they're essentially designed to make this line up. All right, so a common worry with procedures like this is instability. Inverse probability weighting has a reputation for extreme variability, in particular when overlap is low, meaning essentially that there are some units for which treatment is extremely rare. And a lot of people talk about a sort of famous simulation study of Kang and Schaefer in this context. But in part, this is kind of misleading because it's a bad example. And Robbins and co-authors had a really nice commentary on this point. In summary, in the Kang and Schaefer study, treatment is so rare for some units that estimation of a treatment effect or treatment-specific mean is nearly impossible. Remarkably, an imputation estimator still works. And if you tweak the experimental design just a little, you simulate something slightly differently, this falls apart and no estimator works anymore. So we really probably shouldn't be using this example to decide whether inverse probability weighting works or doesn't work. On the other hand, this isn't the only observation that inverse probability weighting can be a little more variable than we'd like. We should probably also blame what I call the usual inverse probability weighting workflow. And that's kind of a two-step process where the first thing we do is we estimate the propensity score by regressing a treatment indicator on the covariate. And then we use its reciprocal to form inverse propensity weights. And the problem with this approach is basically that inversion dramatically inflates errors when the propensity score is small. If you just sort of do the arithmetic and you subtract the reciprocals, you get the product of the values in the denominator, which will tell you that whenever the propensity score is small, errors can get extremely large. All right, so we may be in a position where we want kind of an alternative workflow, and I'm going to talk about one I'll call the balancing workflow. And we're going to start from kind of an obvious place, which is just looking at the error of the AIPW estimator. It really, so it has two terms. Well, we're going to look at a two-term decomposition. One of these terms is basically an average of mean zero stuff. And, by central limit theorem or something, it'll be fairly manageable. The more worrisome term, sort of imbalanced term, in which error arises primarily from a difference between averages of the treated arm value of the regression error function, we see here, and the weighted average of the natural arm value of that thing, we see here. So basically, error arises from our weights failing to do the job we asked them to do. And so we call this difference the imbalance in the regression error function. And so the sort of balancing idea is, if we think that regression error function will be in some set, we'll call that set a model for the regression error. we can choose weights that control the maximal imbalance over that model. So that's just the maximum of this error term over all sort of candidates for the regression error in our model. And there's a nice minimax approach based on this that accounts for the mean zero term as well, in which we minimize the maximal mean squared error of our model. And that's pretty simply just the square of the maximal imbalance plus a term proportional to the squared norm of the weights, which keeps some of this sort of extreme weighting phenomena from happening. So specifically, this is conditional on design mean squared error, where design means covariate and treatment. And it's maximal in the sense that it's the worst case over both regression error functions in the model and over variances bounded by some sort of tuning noise level parameter, sigma squared. So if we think about the weights a little, they're essentially method of moments estimates of the inverse propensity weights. And by that I mean they approximately solve a set of sample moment conditions. Those are the approximate balance conditions for the functions in our model. That is, we're equating our weighted natural arm value with our treated arm value. And the inverse propensity weights solve the analogous population balance conditions. And they do it for all functions in the model M, and they do it for all square integrable functions. So one of the nice properties of an estimate like this is it's a direct estimate of the inverse propensity weights. There's no error inflating inversion step in this workflow. And as a result, we get pretty stable estimates, even in problematic examples like the King-Schafer problem. So let's look at what happens a little more concretely with some of this stuff. So if we have discrete covariance, we maybe can get away with a completely general model. That is a model that says our regression error function could be any function of the covariates outright. And if we let things be this general, the maximal imbalance will be infinity unless we weight treated units so their empirical covariate distribution exactly matches the whole sample. And the point is, because we're completely unconstrained, if there's any difference at all, we can just sort of blow up that difference to infinity. This is what post-stratification does, this sort of exact matching. And so these are weights that are commonly used to sort of adjust non-representative surveys and things like that. Okay, so, sorry. If covariates are continuous, we can't do this. And the reason for that is no two units will have exactly the same covariates. So we need there to be a sense in which two empirical distributions are sort of close enough, even if they don't line up perfectly. And essentially this means we need some kind of continuity in the models we consider. And so we can control imbalance in models that limit discontinuity, some examples being, say, functions with a bounded derivative or two, or functions of bounded variation. And this isn't like a weird requirement specific to balancing estimators or anything. It's really just a requirement that we can learn about a function from its samples. We need the same to do any kind of estimation. So if we have enough continuity, then we can prove some pretty strong optimality properties for estimators like this. In particular, we can prove asymptotic efficiency. So if we choose weights minimizing conditional mean squared error for a model that's convex, uniformly bounded, and admits a uniform central limit theorem, our estimator is efficient under three conditions. The first is a kind of overlap condition, that the inverse propensity weighting function is square integrable. The second is that our regression is mean square consistent, which hopefully you should be getting from your regression. And the third, which is sort of the strong condition here, is that our model is a valid model for our regression error, meaning that our regression error function is either in the model or in sort of a scaled up version where that scale is constant order. So, so this is nice. For those who aren't familiar with asymptotic efficiency, essentially it means that the usual confidence intervals are asymptotically valid, and they have minimal length among asymptotically valid intervals. So this really lets us do inference pretty much however we want. We can form walled type intervals where we just take our estimate and like plus or minus 1.96 times the standard error, or we can do the bootstrap, pretty much anything that would work for a sample mean. So if we have these conditions, basically everything becomes pretty easy, and we can do inference straightforwardly. But of course, to actually use this thing, we have to sort of choose our parameters so all this stuff works out nicely. And we have 3 to choose. The first is our noise level parameter in our Minimax problem. The second is our outcome regression estimator. And our third parameter is our model for its error. And so the good news about this is that the estimator is adaptive. It's sensitive to properties of the regression error that aren't baked into our regression error model. And that means that we don't really need to get that model perfect, which would be pretty difficult. I'll give you a bit of the flavor of these adaptivity properties. Basically, the procedure behaves a bit like we had perfectly modeled a couple properties of the regression error. One of them is consistency, say like the rate at which its mean squared error decays. And the second is essentially its smoothness, like maybe the rate of decay of its Fourier coefficients. We have this in RKHS models. And so that sort of tells us that even though we sort of think of M as the class of all regression errors we could deal with, and it would be nice to have it be right, we don't need to get it that right. And we kind of have the same deal for the noise level sigma. The estimator isn't too sensitive. You can of course screw it up if you throw like sigma 10,000 in there, but basically in practice we usually just use sigmas 1, and it works pretty well, and the theory is basically justified. And I guess as a third point, we actually don't require all that much of the regression error in terms of its consistency. So we don't need to do a great job there either. And so the good news here is basically that we do pretty well with reasonable default parameters. And that's important because we don't really know how to automatically tune and estimate sort of more optimal ones. And this is a challenge in this estimator in particular, but really sort of throughout causal inference and semi-parametrics. We don't really know how to do tuning for our ultimate goal. All right, so let's move on to what's probably the most practical consideration of all, what we actually want to estimate. And I know I'm certainly guilty of sort of not quite knowing how to estimate the thing I wanted and estimating something that's sort of feels similar enough just because I sort of had the code or knew how to do it. And the great thing about working in this framework is that estimating many other things is a trivial change. It's often just one line of code, so we can more often just sort of do what we want. And so some examples of the kind of things we can do are, say, the average treatment effect. Well, that's not that different. The average policy value. So if we had a policy for assigning treatment to people on the basis of their covariates, we could estimate how well that worked. If, say, dose is continuous, we could estimate this average slope of the dose response function. Generally, the framework we're working in is we can estimate a linear functional of the regression function, which we'll call H, that varies with the covariates and treatment level. And so this isn't just sort of a drop-in change code-wise. If you were to substitute H for what I was calling treated arm value earlier in the talk, basically it all goes through, we have the same theoretical results and everything. And in this more general setting, the inverse propensity weights generalize to the Riesz representer of our estimand. And what that means is the inverse propensity weights solve sort of exactly the condition that we've wanted before. The average of H now at a function f is just the weighted average of the natural value of f for all mean square continuous functions. So this is kind of the analog of the condition that defines the inverse propensity weights. And so it's maybe not immediately obvious that this has a solution, but when our estimand is mean square continuous as a function of the regression function m, the Riesz representation theorem guarantees that the solution exists and that it's square integrable. So essentially, the kind of overlap we need is really just saying that the estimand that we're interested in varies continuously with the regression function. So that's actually not strictly necessary. We can get away with estimating some discontinuous functionals, things like the conditional average treatment effect at a point, by using this approach to estimate a smooth approximation. And so the idea is, if we have the conditional average treatment effect at a point, it's not really an average over anything, so none of this stuff really works, but we can approximate it by an average over sort of a little bump around the place we want to estimate it. So basically we smooth by convolution with some sort of kernel, and we can apply the same techniques. And by sort of varying the bandwidth of the kernel, we can sort of vary how easy this thing is to estimate versus how close it is to the like Kate itself, rather. Yeah. Okay, so that kind of closes the story I wanted to tell on sort of what we can do with this estimator. And I want to talk a little about kind of the principles behind how it works and the sort of folkloric tradition it comes out of. So balancing folks, or at least the folks I know, I have done this in the past, tend to emphasize basically three principles. The first is directly balancing the sample, not the population. The second is sort of balancing the right model, balancing what we have to balance, not just a convenient one. And the third is estimating the inverse propensity score, not its inverse, the propensity score. And these are all kind of slogans, but there's some, so I'm gonna give a bit of interpretation to them. By the first one, basically we mean we solve sample moment conditions, the sample balance conditions that we need to make our error have estimator have small error. We don't say estimate the propensity score, which balances the population, that then indirectly balances the sample because the sample converges to the population. And as far as balancing the right model, the idea is if people are focused on modeling the propensity score, they sort of forget about what they want the inverse propensity weights to do, and they get a propensity score estimate that may be close to the propensity score, but not in the right sense. And the third, I guess, is fairly self-explanatory. And so these are the principles that I think we say are why balancing works and why balancing is a good idea, but it's not really clear that we need all three. And as a bit of a thought experiment, we can sort of kill the first by cross-fitting when we estimate the weights. But what I mean by this is we can minimize conditional mean squared error just as before, but we do it for half the sample. And by doing so, we get an estimate of the inverse propensity weighting function. And then we can just evaluate it on units for the other half of the sample. So the only reason we would get any kind of balance here is because our first estimate is an estimate of the inverse propensity weighting function, and that would balance. So it kind of raises a question like, is this balancing, right? So it violates our first principle, but it satisfies our second and third. And it's maybe not super relevant that it's balancing or not. One question is maybe, is it better or is it worse? Because intuition that sort of justifies sample splitting about a phenomenon called own observation bias suggests it might work better. But people sort of...
You have about 5 more minutes left.
Thank you.
Yep, sure.
People sort of hold up directly balancing the sample as the reason balancing works. So we do have evidence that very similar methods work quite well, both in theory and in simulations. So either both are true, or we really don't know. So we sort of have these intuitive principles that tell us that we should cross-fit and we should directly balance the sample, but we can't do both. And we don't really know when to prefer one over the other. And that sort of takes us to where we are today as a community. I mean, historically, there's been tension between folks who emphasize simple balance properties, like the sort of exact balance you get from post-stratification, and those who sort of emphasize semi-parametric efficiency and all of the sort of technical tools that have developed around those ideas. But in the last decade, with sort of more general notions of balance, it's become harder to see the boundary between these approaches. It's less clear what a balancing estimator is, and what a sort of traditional estimator is. So nonetheless, there's still kind of a stereotype that balancing estimators and semi-parametric estimators have fundamentally different robustness properties. So for balancing estimators, we might say something like, oh, they're optimal for the observed design, which is great because that's the design I have. And for sort of semi-parametric estimators, we may say they get a lot of double robustness by sort of thinking about averaging over a bunch of possible designs that we could sample. And the truth is, really, these stereotypical properties may just be ones that are the easiest to prove. It may well be that you know, that we can prove one or the other using some sort of more involved arguments that haven't quite appeared yet. And that's kind of, it puts us in an interesting state because basically there's a lot of, like, these are both desirable properties. And I think the properties people like about balancing estimators and non-balancing estimators are both nice. And we sort of know how to make them happen, but we don't know what we have to do to make them happen. There's really a lot of work to be done in understanding exactly how these properties arise and whether they're compatible or we have to make some kind of choice. And this really isn't work for sort of one faction, you know, balancing folks or non-balancing folks. It's really sort of between balancing and not. It's work for all of us. So thanks for listening, and thanks to the organizers for the opportunity to say my piece. I'll show some references and take any questions if time allows.
Thanks, David, for the fantastic talk. Guillaume, do you want to ask a question?
Yeah, so maybe one quick question. So in work in observational studies, there's kind of the Rosenbaum tradition that has developed its own kind of way of doing sensitivity analysis in this setting. And recently, we've seen some work on sensitivity analysis for IPW estimators, like I'm thinking about work by Zhao and co-authors. Yeah. So I was thinking, is there kind of a movement going through kind of thinking about how to get sensitivity analysis to work in kind of this balancing framework, or does that already exist?
I mean, so like one argument you could make is that sort of sensitivity analysis is about the difference between estimands and estimators. So like the framework for the estimation is largely irrelevant. Of course, these things are coupled in some of these traditions. There's also, you can sort of go at it the other way, right? Like sensitivity, like a lower sensitivity bound is a parameter. And then, you know, you could probably find a balancing estimator for it. I haven't really seen much on much that tries to use balance as a sort of sensitivity notion. I guess, I mean, it would be like what balance fails to control, right?
Yeah. That's kind of what I was thinking about. Or maybe what happens if the true class. So you mentioned that you don't actually need to know exactly the right model class M, that you're kind of like robust to this. But so that could be like one direction in which to look at the sensitivities. Like, well, if it's not right.
Yeah, so there
happens?
may be ways of sort of embedding like kind of fundamental uncertainty into this kind of minimax framework. I haven't seen it yet. That might be cool. Yeah.
Great. Let me see if we have other questions. No, I think that's about it. Yeah, thanks for this great talk. It was very, very interesting.
Okay, yeah, thank you again, Karthika and David. So let me share my screen. So next week, we're very excited to have Joris Moy from the University of Amsterdam, who will present Joint Causal Inference, a unifying perspective on causal discovery. We're very much looking forward to that, and we hope to see you there. Thanks for joining us.